What's the second thing we can learn from the spectrum? It's the temperature. We can tell what the temperature of an object is based on the pattern of light it's giving off. So here's my question. What is temperature? When we talk about the temperature of something, what are we talking about? What are we actually measuring about that object if we're talking about temperature? What does temperature mean? Yeah, how hot or how cold something is. How hot or how cold something is. But it turns out that's not actually what you're actually measuring, okay? It turns out what you're actually measuring when you're talking about temperature, like how hot and how cold is kind of like how we're feeling. And somebody's on the right track right there. What you're actually measuring is the random motion of the particles of a substance, okay? And we don't normally think of it that way because the particles of a substance are very, very, very small and microscopic, right? But, let's say that I was the particle in a substance. If you zoom in far enough that you could actually see me, I'm not just sitting here. Like if we look at the air in this room or your room or wherever you're at, the air particles aren't just sitting still. They're jiggling around, right? They're jiggling around. Now, does anybody know what a high temperature means? Does anybody know what happens to these jiggles if we were to raise the temperature of this gas? What happens to these random jiggles? Yeah, they go faster. So a higher temperature would be something like this. And a lower temperature, if you could see the particles, they're jiggling around slow. So that's what temperature is, okay? What unit are we going to use for temperature most of the time? Well, what's the dumb everyday unit of temperature that Americans use? What's the dumb unit of temperature that we use? Maybe dumb is a bit strong. Yeah, don't worry if you can't spell it. Fahrenheit, right? Fahrenheit. Fahrenheit is not a very good system to use for temperature. And to understand that, we need to know what is Fahrenheit based on, okay? Because every thermometer is basically the same. Like all thermometers, just think of like a typical thermometer, like a classic thermometer. It's just a tube of glass with a substance in it that fills it up as it gets hotter. So you couldn't use any system on that same thermometer. They're all basically trying to tell us the same thing. But let's say you had a blank one and you wanted to set it up as a Fahrenheit thermometer. Does anybody know what the reference temperature, and by that I mean the temperature that the thermometer is based on for Fahrenheit? Do you guys know what Fahrenheit was originally set up based on? Like you needed to have something with a known temperature that you could stick the thermometer in to know where to put the markings. It's based on human body temperature, or at least it originally was based on human body temperature. So it was originally set up so that a human body would be 100 degrees Fahrenheit, right? And if you had a blank thermometer, you could turn it into a Fahrenheit thermometer by sticking it in your mouth and then marking off your temperature as 100 degrees. Does anybody know why that's a bad thing to base a thermometer on? Why would it be a bad idea to base the markings on your thermometer on human body temperature? Why would that be bad? It's like some people are getting it. Yeah, because when you base your thermometer on a reference temperature, you need it to be on something that stays the same. And we have two problems, and you guys have pointed both of them out. Number one, your body temperature changes throughout the day. So depending on when you set up your thermometer, you'd get a different temperature marked as 100 degrees. And also, every person is different. So every person who sets up that thermometer is going to get a different temperature. And you can do things to make that better. Like you could take a group of people and get their average temperature. But that's still no guarantee that the group that you contain is all going to have, maybe you didn't know it, but a lot of them were sick, right? So human body temperature doesn't make sense to base your thermometer on. So Fahrenheit thermometers are not guaranteed to be the same. And we've changed what that's actually based on. It's based on something else for modern Fahrenheit thermometers, but it's still not going to be a perfect match, okay? So Fahrenheit's not that great. What scientifically, the only reason that people in the U.S. like Fahrenheit is because that's what we grew up with. It's like inches and feet. We grew up with it, so we're used to it, so we kind of know. If somebody says 70 degrees Fahrenheit, you know roughly what that is, right? But if we had just grown up with a better system, that's the one that we would have been used to. And what is a better temperature scale that's used by most of science? What's a better temperature scale? Actually, some of you guys mentioned it earlier. Celsius is better, right? Celsius is better. Degrees Celsius are better. And it's better because of the reference temperature for Celsius being a better thing to base a thermometer on, right? So here's my question. Do any of you guys know what the Celsius thermometer is based on? Like, does anybody know what we base like 0 degrees and 100 degrees on for the Celsius thermometer? It's not the human body. It's a type of substance. Super important substance. It's water, right? It's water. And to be a little bit more specific, 0 degrees is the temperature that water freezes at, and 100 degrees is the temperature water boils at. So if you want to set up a Celsius thermometer, you can just get a bucket of water, put the thermometer in it, raise the temperature until it starts to boil, mark that as 100, and then lower the temperature until the water freezes and mark that as 0 right when it freezes. And yeah, that's going to be a lot more reliable, right? Because if I have a bucket of water and you have a bucket of water and we're setting up those thermometers right here, we're going to get the same temperatures on the thermometer. So if we try to do experiments with these thermometers, we need them to be the same so that we can compare results. If they're not the same, no results can really be compared. And that's a lot better. So you can get a much more reliable thermometer using water. But it's still not perfect. It's still not perfect. And to understand that, right now, not everybody in this class lives in the same place, right? Not everybody in this class lives in the same place. Do any of you guys, like right now, where I live, we're basically sea level. Any of you guys live somewhere where you're kind of above sea level? I'm going to guess probably not very many of you, because you're probably all kind of near me. But if you did, does anybody know what happens to water when you try to boil it at a really high elevation, like up in the mountains, like Colorado or something? Does anybody know what happens when you try to boil water there? It boils at a different temperature. Yeah, it boils at a different temperature. And that's because it turns out boiling temperature for water depends on air pressure, okay? Because the air pressure is different up at the top of a mountain, air pressure is different at the top of a mountain, the temperature water boils at and freezes at is going to be different. And so that means if I set up my thermometer here at sea level and you set up your thermometer over in Colorado, we're going to have different thermometers again. So it's not perfect, but it is a lot better than using something like human body temperature. Instead, there is an even better temperature scale, and that's the one that's typically used in astronomy most of the time. Although, don't worry, I will say some temperatures in Fahrenheit as we go along. But does anybody know what that last scale is? What's that last scale that's even better than Celsius? Kelvin. Okay, and I'll write that down because not everybody knows that one. So this is one that's pretty much almost exclusively used in science. And the reason that scientists like to use Kelvin for temperature instead of Fahrenheit and Celsius is that it is a lot more exact, okay? And that's because of what it's based on, okay? Now, what is it based on? It turns out, remember, temperature is about the jiggles. Temperature is about the jiggles in the substance, right? Kelvin is actually based on a special property of the jiggles itself, okay? So what I want you to imagine is we took the air in whatever room you're in, and that we got these random jiggles going on. What did we say happens to those random jiggles if we got the air colder? If we got the air colder, what's going to happen to these jiggles? Don't make me jiggle around for too long. Yeah, they're going to slow down, right? They're going to slow down. And if we kept lowering the temperature of this substance, that jiggle would slow down even more, right? And eventually, it would probably turn into a liquid and then a solid. But even in a solid, there's still a little bit of jiggle in there. It's just really slow. But let's say I keep lowering the temperature. It would keep getting slower. But if I keep lowering that temperature, what would eventually happen to this jiggle? It would stop. And then, here we go, you can't be any slower than stopped. So that means the air in your room has a lowest temperature it could possibly have, where you can't lower the temperature any less than that, right? Now, it turns out we can do that for any substance. For any substance, sorry, I'm getting another case of freezing display. Haha, okay. Now, if we took water instead, it's jiggling, right? If we lowered the temperature of the water, that jiggle would eventually stop. So there's a lowest temperature for water too. And if we took an even totally different substance like gold, there's a little bit of jiggle inside every piece of gold. If we got that gold cold enough, we could find a lowest temperature for gold. So every substance, if you lower their temperature enough, all of their jiggles will stop, and then that's the lowest temperature you can make that substance. Now, it turns out, what we figured out is that lowest possible temperature is the same temperature for every substance. Every substance that exists has the exact same lowest temperature. And that means that nothing can go lower than that one certain temperature. That's the minimum possible temperature for the universe. Does anybody know what we call that minimum possible temperature for the universe? Yeah, all the particles stop at the same temperature. I'll go ahead and tell you what it's called. It's called absolute zero. Okay? It's called absolute zero. Yeah, and actually somebody got it. The delay. Good job. Good job. Now, so that temperature is what Kelvin is based on. And it turns out it doesn't matter what the substance is made out of, and it doesn't matter where it is, or what pressure it's in, or what the properties around it are at all. The lowest temperature is always exactly the same. So if you base your thermometer on that, then your thermometers would always be the same. And so that means that Kelvin thermometers are always identical, okay? So to distinguish between those, things like Fahrenheit and Celsius are called relative temperature scales because you're not always going to get the same thing. It depends on the situation. But Kelvin is called an absolute temperature scale because it's based on something that never, ever changes. So Kelvin temperatures are what's typically used in science, especially when you need the temperature to be really precise. Now, check this out. Check this out. There's a benefit here. If we make the absolute bottom temperature 0 Kelvin, what kind of numbers do we not have to deal with in that temperature scale? If the lowest possible temperature is 0, what kind of numbers do we not have to worry about? They're always a pain in the butt. Negative. There's no negative temperatures in Kelvin. So all you really got to know here is that a bigger number in Kelvin just means a hotter temperature. Okay? So for example, here we go. Let's say we had object A and object B. And object A was 500 K and object B was 2500 K. So 500 Kelvin and 2500 Kelvin. Don't overthink this. Which one of these is hotter? A or B? Which one's hotter? Yeah. B is hotter because it's got a higher number of Kelvin. Okay? Oh, and by the way, a lot of times people forget that this is a temperature because they're not used to Kelvin. And also because there's something missing here that we normally see on temperature scales. When we talk about Fahrenheit and Celsius, it's always 35 degrees Fahrenheit. And you have that little circle, right? Same thing with Celsius, 35 degrees Celsius. But in Kelvin, we don't say degrees, okay? We just say Kelvin. So this can be read as 500 Kelvin or 500 Kelvins. Both of those I've heard is acceptable. But just remember, when you see just a capital K after a number, you're looking at a temperature.